Totally fine. All right. Yeah. So I'm going to be talking about post-quantum cryptography. And again, please feel free to interrupt me if you have any questions or anything like that. This is a pretty small meeting. Um, so I'm going to basically talk about three things today. I'm going to talk a little bit about the quantum cryptography threat and threat modeling that. I'm going to talk about the PQCA, and then I'm going to just briefly give you some details if you want to look at what we're doing. So let's get started. Um, so the whole premise of this, and which I'm assuming you all are, generally familiar with, is that sufficiently large quantum computers can break essentially all traditional public key cryptography. And what I mean by traditional is sort of, all the standards that are in place today, pretty much everything that people use today that's public key can be broken with quantum computers. I'm not going to go into the details. I can if you want, but probably not something we should really dive into today. So, so why quantum? And I will say that this was not my slide originally. This was actually an engineer slide, but anytime you can sneak in quantum complexity to an engineering talk, you have to have fun. Um, but sort of they're easy problems, right? If you're familiar with complexity class P or BPP, things you can do efficiently in polynomial time. And then there are hard classical problems, which is, complexity class NP. Um, and the thing is, what we think is that sort of the, you know, the easy quantum problems are much larger than the easy classical problems. And unfortunately, a lot of modern cryptography lies in this intersection of um, easy quantum problems and potentially hard classical problems. So I'm not going to go into quantum computation too much, but the power of quantum computing is that you can compute things in what's called superposition. And this goes back to the Heisenberg uncertainty principle and physics. But, um, you know, bits can be in a superposition of multiple values. They can be entangled. And well, it gets very complicated, but there are a lot of neat things you can do with quantum computing, and I would definitely encourage you to take a deep dive if you're interested. So, one of the most common, I should say, separations between quantum and classical computing is factoring. Are people here familiar with Shor's algorithm and factoring?
Can I say sure? Sorry.
Yes.
Ah,
Yes.
Sorry.
Acceptable, Mike. We'll take the puns when we can get them. Um, so Shor's algorithm allows us an exponential speed up for factoring in discrete log problems. So the best factoring algorithm, is approximately, 2 to the d to the 1/3, where d is the number of digits or bits. Whereas Shor's algorithm is a constant times d cubed. And these are sort of hard to, think about because big numbers are typically very hard to think about. Um, but I'll give you an example. So, does anybody know about how many atoms there are in the universe?
3.
Great guess, Dan. Um, no, so there are about 2 to the 300 atoms in the universe. So if you set D to be 1,000, uh, you know, using a classical algorithm, if you had every atom in the universe as a computer, it would still take eons, basically. Whereas, D to the cubed, is a billion, right? And that's a level of computation we can do today. Great guess, Benjamin. You win the Price is Right over Dan. Um, I'll even give you credit for 4 factorial, which is even closer. Um, so just thinking about these sort of exponential speed ups and exponential numbers are illustrative for thinking why this is so destructive to cryptography. Basically, you can't have a crypto system secure against anyone if there's a polynomial attack algorithm for it. So as I said before, essentially all of modern cryptography that's used today is at risk. So, if you use ECDSA or DSA, all essentially elliptic curve algorithms are broken. So this is a problem, right? Someone with a powerful quantum computer can just break everything. There's nothing you can do. You can't raise key sizes large enough to stop this. And that's sort of the fundamental point I want to make here. I don't think I need to tell you that the world depends on cryptography. It's getting more and more important. And, some things are quite frankly scary, like, to me at least, things like self-driving cars with over-the-air updates, where if a hacker could take that over, it would absolutely be catastrophic. But, I don't think I need to convince you of this. So there are a lot of potential attack vectors that someone with a quantum computer could do. Um, Obviously fraudulent authentication, forged digital signatures, but really the more problematic thing is breaking encryption. And this really gets into what's called the harvest now decrypt later problem. Have people heard of this before? Some people, I see a couple nods. Excuse me. If you're not familiar with this, what this basically means is people today are recording your data as you send it across the internet, right? You know, the US government has an entire nuclear power plant that is ostensibly hosting a data center, just to give you an idea of the magnitude of this. And they're not the only ones doing this. The problem is, if people are recording your data now and all your encrypted traffic that's going across the internet, suppose there's a quantum computer that comes along in 5 years. Well, if you need your data to be, secure for longer than 5 years, you have a real problem with that, right? And so that's why sort of quantum security has been somewhat of a guessing game, as we'll go into later, because you need to adopt quantum computers, long enough in time that your data still going across the internet will, you need to move to quantum before that sort of time expiry happens and people can build powerful quantum computers. So this is a fun chart I like to show. So I'm a computer scientist, not a physicist. Don't ask me when I think a quantum computer will be ready, because that is a question for physicists. But this is a chart where, they polled a bunch of quantum physics and quantum computer building experts, and they asked when a powerful quantum computer would be built. Or they asked these experts when they thought. And you can see sort of the distribution, right, of percent likelihood and time. So there's not a huge consensus, but, generally speaking, lots of folks are pretty scared about the 15-year time frame. Virtually everyone is scared about the 30-year time frame. And this is a real problem in some fields like finance, where in some cases you're required to hold on to data securely for 30 years. So, this is one thing to think about. So how do we deal with this? Well, the answer is quantum safe cryptography. So there are cryptographic schemes which we think to be secure against quantum computers, as well as classical computers, obviously. but they rely on a completely different set of mathematical problems than traditional public key cryptography. Um, there's a drawing of a lattice here, and lattice cryptography is one of the solutions proposed here, probably the most popular solution. I can answer all your questions on lattice cryptography if you like, but I'm not going to go into it today. So we need to switch to new protocols. I will say there is an excellent course from IBM on this that they are planning on hopefully contributing to the PQCA. So hopefully we will have a lot of this content in the future. But check it out if you want to learn sort of more about all of these crypto systems. So how is this working? Well, there's been a huge standardization effort around post-quantum cryptography. It's been one of the biggest efforts in a long time. A huge amount of review by cryptographers. There have been a lot of schemes proposed, a lot of schemes broken. And we're supposed to have the first set of winners this month. I'm still waiting for the meeting where they announce them like the morning before, and I haven't heard it yet, but hasn't happened yet. We should have a first round of standards this month, and it will likely be these 4 protocols: Kyber, Dilithium, Falcon, and Sphinx. The first 3 are based on lattice cryptography, and Sphinx is a hashed-based signature algorithm, if you're familiar with those. So what are the issues with this? So I'm going to paint this with sort of a broad and general brush. Computation is not that much more expensive with post-quantum cryptography than traditional cryptography. These lattice-based schemes are, actually quite efficient, and most people are using them. However, keys, ciphertexts, and signatures are much larger in size. And this is, in some applications causing trouble, because if you need, if you have an application where you have to process a lot of signatures or store a lot of signatures, then, or maybe do a lot of repetitive key exchanges, this can be a problem. And usually the factor is something like an 8 to 10 factor. For modern, TLS use, maybe this isn't a problem. But if you're running a blockchain and you're storing a bunch of signatures on the blockchain, this could be very problematic if the thing you have to store most on your blockchain blows up by a factor of 8 to 10. So, the hardware timeline, and I know you all are very interested in hardware, obviously, is really interesting to me because, it's hard to put hardware into practice. I don't need to tell you all that. You all can probably you all can definitely tell me more about that than I know. But to really roll out, hardware that uses post-quantum cryptography, we have to have finalized standards that everyone trusts because we can't really change them once we put them in hardware. The hardware has to be developed. The hardware has to be rolled out. And then, because of this harvest now, decrypt later threat, this all needs to be done, not only before quantum computers are out, or at least powerful ones, but also, in time that people can switch and still have their data be secure for the amount of time that they'd like. So, this all could take quite some time, and people may have long life expectancy for their data security. So
Hart, it might be worth mentioning that in the last time meeting we talked about some of this stuff. Although obviously we do care about hardware, the general feeling is that most of the pieces that are involved with confidential computing is around the attestation, and most of that is actually in firmware or microcode. So we're hopeful that in our sphere of interest, most of this does not require hardware changes to be implementable, which is obviously a great win from our point of view. It doesn't
Yes,
everything, but that may help us, right?
that's fantastic. And yeah, I have a slide about cryptographic agility later, so that is wonderful to hear. Um, yeah. So Alec, it's not all network traffic, as Mike correctly points out. It's just the initial TLS handshake. So in a typical interaction with like a website, you use a public key to agree on a secret key, and then you use that secret key, yes, use a public key to agree on a symmetric key crypto key, like an AES key, to handle the bulk of your communications. And so if you're interacting on the web and you're, talking to one website, say for a long time, it means that, this extra traffic is not too much of a problem. Um, for some applications, there are issues with packet sizes and other things, but in general, the communication is not a huge problem. If you are querying lots of different people and have, very short requests, that's when this becomes a problem. Sorry, Dan?
Just building on that question. So all of this applies to public key cryptography, but for the symmetric key cryptography, are there changes that need to go hand in hand with the new algorithms?
So this is a great question. So in theory, yes. In theory, there's an algorithm called Grover's algorithm that essentially allows you to do a brute force attack in the square root of the time, essentially, that it would normally take. So this is not an exponential speed up. This is a sub-exponential speed up. Or I'm sorry, it's the square root of the key. It's half the key length, right? So essentially, if Grover's algorithm had no overhead, then you could solve like 256-bit AES, right, in time proportional to 128-bit AES, right? Because the square root is just a 1/2 in the exponent, right? That being said, we don't know the full efficiency of Grover's algorithm with like this is a polynomial speed up really, with quantum error correction. It might be expensive, so we don't really know how all of this works. For conservative choices, we typically recommend that you use like AES 256 and SHA-512 for quantum security. But doing so and switching to these longer keyed algorithms is considerably less disruptive than changing your public key infrastructure.
Thank you.
So did that answer your question?
It sure did.
Awesome. Great. So before I get into the PQCA, does anyone else have any more questions about, quantum or post-quantum cryptography that I could answer? Nope. All right. Awesome. I'll keep going then. So to deal with this, we've had a number of companies. I think many people on this call are involved with some companies that are involved with this. But we've created a Linux Foundation umbrella project for post-quantum cryptography that we've called the Post-Quantum Cryptography Alliance. I think we are much less creative than naming with you all, and probably a lot less fun. The goal of this is to, advance the adoption of post-quantum cryptography by building high-quality code and really interacting with the research community and the developers as they continue to iterate on quantum and best practices. So we're overall structured in a standard LF project way, very similar to you all. So I don't want to go into that too much. We have a couple projects that I'll talk about. Right now we have the Open Quantum Safe project and the PQ Code Package project. Again, I said, less whimsical names than probably Dan and Mike would prefer, but it is what it is. Uh, and this is, kind of what the scope of the code base is today. So OQS is technically not marked as a ready for production project, but people do use it in production all the time today. We have a huge number of use cases on our website if you're interested. But the idea is to support development of algorithms and to implement and use new algorithms sort of as they move into the pipeline. NIST is not done. Even now, they're going to release an initial set of winners, but they're actively looking for, other schemes as well. So we expect to have a lot more, particularly development side of R&D in OQS. And then we also have what we're calling the PQ code package, which is mostly at this point high assurance implementations of the Kyber standard. And this project has a lot of people that are heavily involved with formal verification of cryptography. So there are a number of, there's a formal verification angle going on here as well, and there's some code around that. So let me see if I can answer the question in chat. So Alec asks, algos that have many individual connections during a workload will be heavily penalized. Algos that get a session key and keep the session key alive for the entire duration will not see much impact. Yes, that's exactly right, Alec. Completely correct.
Well, there's yeah. When you say
Let me just say, I didn't want to sidetrack the presentation here. Maybe we can have discussion after the presentation.
Yeah, because things like session reestablishment is different to rekeying, which may be a lot cheaper.
Sure,
right? So
that's true.
Yeah.
If you store the if you store the session information, that's great. There are some protocols where you generally want to generate a fresh key every time, and there are advantages to doing this. But that's probably out of scope. But Mike, you're exactly right that if you're caching session keys or whatever, then you don't suffer from this. But if you're interacting with new people, or people where you haven't done a public key interaction with before, then it's definitely problematic. Happy to have questions. Like don't feel shy about asking. So awesome. Okay. So as I said, we really want PQCA to have an experimentation angle as well, because a lot of these new standards are coming out. They're still coming out. We want to be able to test them and prototype them and give feedback to the researchers that are developing them about what works and what doesn't work. So, somewhat unique to LF projects, we do have a full research track where we've got code that, we're clearly saying, don't use this in production. This is just for us to be able to test out new standards. So a few more details, a little bit about each of the projects. So the OQS project, all of your favorite standards at this point. There's also an SSL provider. If you're interested in that, that gets a lot of attention and people really like that. And we have also added some really nice demos if you want to see that. So check those out if you're interested. Just a short list of who's involved. We have a lot of folks, a lot of big companies, mostly tech companies at this point. And we'd really like to get, less traditional tech companies involved. Things like finance, more system integrators. but we're very open and happy to have contributions. So if this is something that you'd like to get involved in, definitely let us know. Oops, sorry about that. As I said before, the PQ code package is heavily focused on formal verification. We've got a bunch of folks from IBM Zurich working on this, as well as a lot of folks from the European academic cryptography community. But the goal of this is to have formally verified, extremely hardened implementations. And that's it right now. We're expecting a bunch more projects. We're probably going to have a CBOM project coming in very soon, if that's something you're interested in. Are people from here familiar with CBOMs? So this is a cryptographic bill of materials. You've probably heard of SBOMs. So this is a sort of cryptographic equivalent of that. Just, what cryptography are you using? What implementations? Essentially serve the same purpose as an SBOM, but for cryptography. And so, looking forward a little bit, the goal is to have a complete PQC stack. We want cryptographic agility providers or APIs, libraries, base level implementations, formal verification, CBOMs. We understand that, we need to make it easy to use and switch to PQC, or people just won't do it, or they won't do it well. And this requires, a lot of tooling and a lot of ease of use software, as well as the core protocols. So that's our goal. And I think this goes back to Mike's point on cryptographic agility. So yeah, I've got a little bit of project information here. If you want to check it out and see what we're doing, we're an LF project. We're completely open, obviously. So, feel free to check it out and join. And that's about it. That was about right on 25 minutes, I think, Dan. So
Expertly done.
Happy to answer questions if anybody has them. And I can post my contact information in the chat, or you can find me, and I'm always happy to answer questions later as well. Any
so
questions?
This is really, really great. Thank you, Hart. I think you've dealt with quite a lot of the questions we already had. I think the interesting stuff is, around where, as you said, we reckon it's mainly attestation where we care about this, because that's where the asymmetric crypto generally happens in confidential computing. And I think there are going to be questions like how. One of the things you need to do with attestation, of course, is verification as well. So is there impact for verification times for attestation measurements that we're going to need to think about for attestation services? Is that a fair question? And whether hardware will come along that'll help if that's the case?
Yeah. So yeah, people are optimizing hardware for this stuff. Definitely, that's already happening. And as I said before, the verification time for attestations won't go dramatically up unless you're doing fancy cryptography for your attestations. If you're doing like zero knowledge proofs or trying to do post quantum snarks, those are much more expensive than classical. But this is really in the research domain, and you're probably not doing that. For basic signatures or other simple attestations, it's not really the time that goes up. The time is very fast. Like verifying a lattice-based signature is super fast. The problem is the key sizes again. Just having to store keys and deal with key management is the real issue.
Yeah, there has been some discussion of things like Z or ZPKs as part of attestation measurements. I think there's some really interesting verification. So there are some interesting questions around there, and I think it's something that we need to keep an eye on. So that's really helpful. I'll step aside and let other people ask questions. Thank you.
I'll comment before going to the next question that I think ZKPs are the wave of the future. You know, because we're going to want, as more and more stuff becomes online and digital, we're going to want more and more privacy. Um, and so I think in the future, you're not going to present a credential. You're going to present a ZKP that you have a credential. Um, the EU is strongly considering this already for their, digital ID solutions. So I think it's just a matter of time. And sorry for the sidetrack. I think Fritz is next.
Yeah, I mean, I want to ping in on the same thing that Mike said, and so there's a slightly different angle also to the performance thing, right? So it's not. I don't think it's correct to say it's gonna be fine with scaling completely, because if you look at kind of the station, if you want to do it fully post quantum, basically the crypto processors have to support sending a PQC at the station at a high data rate, right? And so depending, of course, on the device, if you just have to send one to the station, sure, it's maybe going to be a little bit more. But if you have a device where you expect to send thousands or tens of thousands, I don't know where we want to go in 10, 20 years, right? Of at the stations every second, then suddenly every single bit of percent that you increase in performance will break your neck at every single step. And so I think it's going to be interesting to keep in touch between yours and our groups, because even if for most of parts maybe performance might be done or might be feasible for lots of these software projects, there is still going to be a lot of hardware rooted elements that we need to support here, right? So and I think all of these requirements that CC maybe adds on top might also make it more difficult. So yeah, I would like to see more or us kind of meeting at least every half year or so to just kind of stay in touch and see what new use cases we have and as it may arise or something. Maybe we can come up with some process there to keep talking.
Yeah, absolutely. That would be fantastic. I think Mike.
Yeah, so I'm kind of wondering, are there any shortcuts where if you're doing if you're doing signatures, which is what we're talking about Cardinal here, and you're obviously sending a certificate, I guess that you may not need to send the entire key in each occasion, right? If you're having multiple communications,
That's right. Yeah.
So you may be able to shortcut at least some of the transport costs there, right?
Yeah. I mean, the thing is, it's not just the keys that are larger; it's also the signatures themselves.
Yeah. Okay.
So you get hit a little bit there as well.
Right. And they same sort of factor in terms of size, larger?
A little bit less, but you can't do things like in a BLS signature, for instance, right? You can have a signature that's a single group element, which is very compact.
I'd love to see if there's been some easily. I mean, I'm not a cryptographer or a mathematician, to be entirely clear. I'd love to see if there's some easily accessible and digestible work on what these sizes look like and what work's being done in terms of optimizing, whether it's for transport costs or computational costs and stuff as well, if that's happening within this world.
Yeah, and this is a big thing. There are a lot of people looking at this, like particularly the signature size issue. So there's a whole new mathematical or a whole new set of signature schemes based on a mathematical assumption called elliptic curve isogenies. And these are essentially mathematical maps between elliptic curves. you know, inverting these maps is conjectured to be hard for quantum computers to do. So, you know, these schemes have the advantage that they do have signature sizes that are like almost, you know, relatively comparable to, you know, traditional group-based cryptography. However, the sign and verification times are expensive.
I love it when mathematicians use words like conjectured. He's like, we think it's probably the case, but no one's actually proved it yet. So who knows? But that's a good start, right?
Well, I mean, we can't prove that, you know, we can't
I
separate.
know.
So, you know, we can't prove anything. Absolutely.
I'm being mean. I'm being mean. This is all good
No,
stuff. It's great. Thank you. Sorry, I'll shut up for a bit. I think Dan and
totally
someone else
fine.
got the hands up.
Yeah, no, I'll just follow your lead a little bit on the signatures. Maybe the slide that you had that had the finalists from the competition. I think the first couple were meant for key exchange, and then the last couple were meant for signatures. But it might just kind of help people connect the dots on which algorithms we're talking about. And I think Falcon stayed on the list because it was more compact.
That's
there's
right.
another...
Falcon is a little bit more. Falcon is the most compact lattice-based signature scheme. Yeah, I can try to page back to that slide. This one, right?
Yeah.
Yeah. So dilithium, Falcon, and Sphinx are all signatures. Kyber is a chem. Dilithium is slightly so Sphinx is a hash-based signature scheme. This means it only uses the security of essentially hash function, so probably SHA, which, you know, we widely conjectured to be secure. However, this is a stateful signature scheme, which means it's annoying to implement, and the computation time and the parameters are generally very large. So this is if you want to be extremely conservative and you don't trust lattices. So dilithium and Falcon are two signature schemes based on lattices. There are sort of two fundamental kinds of signature schemes. There's a Lubashevsky and there's a GPV. Dilithium is the Lubashevsky. Falcon is what's called a GPV signature. They're sort of different in how they're done. Dilithium has a little bit larger signatures, but Falcon is sort of a nightmare to implement in a way that's secure against side channels and you know, other attacks.
So a couple of thoughts. Firstly, do we think that when we say side channels may well be different if you're implementing within a trusted execution environment, and it'd be very interesting to see whether people have thought about that and done any work on what the side channel attacks look like there.
They have. So unfortunately, like, using a TE does not help you against like a timing attack very much.
Okay, so a constant time is difficult for this, is it? This sort of stuff.
So Falcon is very dependent on sampling noise in the shape of what's called a discrete Gaussian. This is like very problematic and difficult to do in a way that is both efficient and you know, and resist timing attacks. So like the classic way to sample a discrete Gaussian is to do rejection sampling, and that's not, it's highly timing variable. It's just difficult to get right. So.
Okay, so I had another question that was kind of a follow-on from that one. If other people have questions, please go first, because this is I don't want to be taking all this stuff up. I hope this is useful for other people as well. So my question is,
I just had one thought on the signature stuff, because Mike, you had asked about different tricks to to make that smaller. I think ECDSA has a property that you don't have to send the public key if you're sending the message, if I'm remembering right, because you can extract that from it. Does Falcon or dilithium have a similar property?
No, that
No?
is group magic that is specific to ECDSA. And if you want maximally small signatures, you should use BLS signatures. They're sort of as small as possible.
Okay. Thank you.
Okay, so if I may go back to mine, if that's okay, Dan, unless there's anyone else. And mine was about the encumbrance. So I'm assuming that all these are open source, and that all, because everything NIST is open, is at least IP unencumbered. And I do know there were, in the early days of ECC, for instance, there's a lot of issues with IP encumbrance. How's the field looking generally in terms of patents and all those sorts of nice things?
So NIST generally only picks things that they don't think will be IP encumbered. So this is all essentially clear to go. Okay.
And what about the rest of the field? Is there stuff happening out there, people are being nice about, or, how are these, how's it looking, would you say, in the field generally?
In what sense?
Well, I'm sure there's other people, doing startups and things around, quantum resistant or post quantum. Are we worried that they're going to, significant speed ups or hardware implementations of speed ups that will be IP encumbered, for instance? Because that's a classic area where you've got hardware improvements and performance improvements, and they can be IP encumbered.
Maybe, but most of the work on this has been done in the open by academics. I mean, I would say there's been a real shift over the past, probably 20 years, where basically cryptographers figured out that if you patented your cryptography, no one was going
People
to
don't
use
it,
even if it was better than what existed, right? This is the iconic case. Is Schnorr signatures versus ECDSA signatures, right? Schnorr signatures are just better than ECDSA signatures, but no one used them due to patent restrictions. So, certainly I don't know of any optimizations that have IP protections that are, public. It's possible someone has done things, that are not public, particularly if they're specific to a certain kind of hardware.
That's really, really helpful. I mean, I happened to be involved in the ECC world about 20 years ago, so I was very aware of the of what's going on. That's really helpful. Thanks, Hart. Really like that. Thank you.
Yeah, the big shift away from patent protection. So
cool. Thank you.
Anybody
okay,
else?
I'll just ask one clarifying thing, because you said a minute ago that for minimal signatures we should use BLS, but that's in the context of classical, right? There's not a PQC construct that. Yeah. PQC. Okay.
Yep.
Right. Thanks for that.
Yes. There are, sorry. BLS has a lot of nice properties as well. It's essentially trivially thresholdizable. And that's something that we can't really do nearly as efficiently with post-quantum signatures yet. So.
Is it just me who thinks JLS whenever you say BLS? I think K-pop, and it's just not helping my head. It's just me, right? Okay, that's just fine. Okay.
Or at least it's not me.
Yeah. No, I'm very pleased for you. You don't need it, please.
All right. Well, thanks so much, Hart, for giving us so much of your time today. This is fantastic talk.
Yeah, much appreciated.
We do put all of our and we do put all of our video recordings online on YouTube. And if it's assuming it's cool with you, we will also usually cut out the tech talks and post those separately.
Sure, whatever you like.
Wonderful. Thanks again.
As long as Mike doesn't dub me into a K-pop video.
Now you've given me ideas, you see. The fact that I have a favorite K-pop video says more than it. Yeah, I'll stop. Thanks, Hart.
Thank you all very much for your time. And
Hey, Mike, no more trips to Korea for you. I think we're going to ban you from
I think that's probably best. Yeah, no, that's fair enough.
Anyone here, please feel free to reach out and get in touch if you have questions or if there's something I can help you with.
Thanks again, Hart. This is great.
Fantastic talk. Thank you, Hart.
Yeah, really good.